Good afternoon all. Welcome you back. Um, Now the next lecture will be given by Dr. Parwat Singh Anjana. Parwat Singh Anjana is a PhD in computer science from IIT Hyderabad and a postdoctoral researcher at the Parallel and Distributed Computing Research Lab, Department of Computer Science at IIT Hyderabad. His research interests broadly span parallel and distributed systems. He has primarily been focusing on blockchain technology to develop sound and scalable methodologies for building efficient transaction execution frameworks. So I request him to please come onto the stage and deliver his lecture.
इसको कनेक्ट करना है अगर पॉइंटर यूज करना है तो पॉइंटर यूज करना है यहाँ तो यू हैव टू कनेक्ट हियर ओके ओके द रोड हैव यूज्ड फुल स्क्रीन नहीं स्लाइड्स एक मिनट बनाया स्लाइड शो इट विल इन व्यू स्लाइड्स स्लाइड्स में सर इट विल बी इन व्यू स्लाइड्स second last so mic is there working? Mic is on. So hi everyone. It's not working, right? Is it working? Audience will बोलते हैं और लोग भी हाँ जी ठीक थोड़ा कट रहा है So hello everyone. So I am Parwat Singh Anjana. I'm talking about parallel execution of smart contracts in blockchains. So before joining at Supra Oracle, I was a postdoc researcher at IIT Hyderabad. So this work was done during my PhD. So we worked on increasing the efficiency of the blockchain platform by employing the parallel execution of the smart contract transactions there. So you might already had a lot of background now in the blockchain technology, like what is the smart contract, how blockchain work. So I believe like a lot of the things, basics are clear now. So I will go a further one more level to discuss about what are the challenges and what are the difficulties in blockchain platform. Like you had heard about interoperability in the blockchain platform, scalability, security, and various other aspects. Dr. Shamsundar has covered a lot of things there in the morning. So before I go into more detail of this thing, I'm thinking of giving you a intuition of a smart contract, like how a contract looks like, what are the conditions and terms recorded there. So I will give a presentation of a simple solidity contract for the simple auction, where we will have one bidder, one commodity, and there will be a number of bidders bidding for that commodity, and at the end of the auction, the winner will be given that commodity, and the coin will be transferred to the beneficiary. So Yeah. Let's first look at what will the outline for this talk. So I will briefly talk about the blockchain technology and the smart contract. Then I will talk about the bottleneck and challenges when we talk about like parallel execution of the transaction in the blockchain platform. There are two different techniques which I, with my other collaborator, have proposed. One is based on statistical analysis of transactions. Another one is runtime analysis of the transaction and execution. So if time permits, we will go into more detail of these techniques. Otherwise, I will conclude with the contract and challenges in execution. Yeah. So let's first look at what is the blockchain technology. Like from the definition wise, it's already clear. Like it is a distributed decentralized ledger of records which store the information in the form of blocks, where each block is having pointer to the previous block in the form of hash. From the genesis to block 1 will have the hash of genesis block 2 will have the hash of block 1, and so they are linked with each other. Each block consists of set of transactions and various other parameters like nonce and all those things which Dr. Shyam Sundar have presented in the morning session. So these blocks are added to the chain by the miners in Bitcoin and Ethereum. They are called miners. Basically, they are block proposers. They collect transactions submitted by the client to the blockchain. They form a block. They keep those transactions into a block, execute them, and then broadcast that block based on the consensus protocol called like proof of work, proof of stake, and various other protocols are there. So in proof of work, they solve the mathematical puzzle, and the node which is solving the puzzle first propose its block to be added into the chain. So when a block is proposed, the validator validates that block by verifying all those transactions are correct or not, and state validation, all those things will be done, and then block will be added. So every peer or every node in the blockchain network will maintain the ledger with them. So if anyone want to make any change to the earlier block which was already part of the chain, they require a lot of energy or a lot of proof of work they have to solve from that block to till the current block. So it is kind of like immutable ledger which require a lot of energy from if you talk about proof of work consensus mechanism. There are different type of chains like Bitcoin, Ethereum, Hyperledger Fabric, and Sawtooth, permission and permissionless, consortium, and all those things we have discussed. I will focus on Ethereum blockchain. Let's first look at contract, like a smart contract. So like contract is a computer program or code which record the condition and parameters like state variables in the contract. And when a user invoke a transaction, so it basically call one of the function of that contract which will be considered as a transaction, and it will be executed in the by the node with the blockchain nodes. So this is like you can think of as a in modern blockchain, contract is a interface between the user and the blockchain platform. So it is sitting between both of them. So it is an interface software layer between the client and the blockchain. So examples are like ballot, coin, simple auction, and there are many whatever application we develop that will be a contract. And we already have seen the benefit of this. So let's first look at how a contract looks like. So I hope my screen is visible. Let me zoom in so it will be visible to everyone. So here you can see a simple auction contract. I hope font is visible. Yeah, okay, cool. So this is simple auction contract written in Solidity programming language. The interface you are seeing here is a remix ID, which is used for developing the contract and deploying those contracts in Ethereum blockchain. It provides all the facility. Here you can see like this is the first page of the Solidity interface, remix interface. Here you can write your contract, and all those existing contract will be there. So if you want to try, you can go there and look at those contracts. This is one of the contract which I have with me. This is the compiler which auto-compile those codes. And to deploy, I already have deployed one contract. Let me delete it and oh, no one is it. It's not working. Apa? But the font will be very small, right? Yeah. I hope now it's visible, right? Yeah. So let me delete this contract. So this is the contract, okay? This is the contract I was showing. And to deploy this contract, there are different virtual environment Solidity provide, like injected Web3 and Remix virtual machine, and there are different environments are available. So let's say this is the virtual environment. Here you can see different accounts. So anyone who want to be part of the blockchain, like as a user or as a validator, you have to have account. So your account is kind of like in normal, like you have in banking system, you have your account to transact or to do anything with the banking account. Similarly, here also you need an account. So here some sample accounts are there, and to do any transaction on even on Ethereum, you need to have some fund in your account, like ethers. So here some artificial ethers are given, 100 ethers are there in those accounts. You can use any of this account. Let's say I'm using this account to deploy the contract. So this is auction contract. I will go through the contract later on, but just like let's look at how to deploy this contract. So I'm deploying this contract. It requires several parameter as an input. So I'm giving this 100. This 100 is auction end time. Like this is simple auction. So in how many seconds from the now, the current block, you want to end the auction. So it automatically terminates the auction after 100 seconds. And here is the beneficiary address. One of the address, let's say, I will take another address from here. This is a beneficiary who want to sell his let's say, property or something. So this auction is for that. Just for imagine like this is the case. So he put his property for the sale. So I'm putting this beneficiary address here. Yeah. And now I'm deploying this contract. So this contract will be deployed here. You can see the sign like it is successful, right mark is there. So here you can see low level details about transaction hash and who has initiated this transaction, the gas used, and all those low level details are there. But for just like to have a feel of like this is a contract which is deployed. So after deploying the contract, here you can see the user interface. So this contract has these functions. Okay, auction end is show the auction is over. Bid when someone want to bid for, let's say I'm selecting another user, this user, or he was the owner, I'm using some other user, and let's say he's bidding. He put some money, like I want to bid 12 rupees or something. So this is again bidded. If assume like he after bidding 12 rupees, he want to bid for 5 rupees or something. So he is trying to bid, but this transaction failed because he is bidding smaller than the higher bid already there. So you can think of like these conditions are there in the contract. That's why it was able to detect those things. Now let's say he want to bid more, he bidding 50 rupees or something. This is again successful. Now let's say there's another. Before going to show you another user, let's check who is the highest bidder now. So this address is the highest bidder for this current bid. Now let's say the other user, someone else, is bidding more amount than the 50, is bidding 55. So this transaction is successful because bid is higher than the previous amount. Now you can check the bidder will change. So here you can remember 78 is the end address. DC, the new bidder, is the winner of this bid currently. So assume like now when bid is over, like who is the winner. You can check the auction time whether it is ended or not. And when auction ends, it's saying already ended or something. Yeah, auction is already ended. Yeah. So yeah, this is like how you can see like let's go through the contract first, so you will understand what are the conditions were there which is making this thing happen. So here the beneficiary, which address we have provided with the while deploying the contract. This is the auction end time which we have provided as input. There is the highest bidder and highest bid. The person who is bidding will be the highest bidder and the amount he is bidding for. So these two state variable recording those things. So whenever a transaction is initiated and it is going successfully through the system, it will be recorded into the blockchain. Okay. So this, because these parameters are changing, he is bidding highest bid, so parameter changes, that transaction is accepted, meaning that there is a block which consists that transaction is accepted into the blockchain and recorded into the blockchain. These are the other parameters which is recording, like pending returns. So someone has bidded earlier, his amount was less, so this kind of array, or you can say mapping, is there, key value pair. They are recording what was the amount to refund it at the end, because he has bidded into the bidding and he must receive his amount. Someone else has bidded high amount. These are the events. I'm not going to low level detail of these errors and all those things, but this is the constructor where we have supplied those bid end time and beneficiary. It is stored those things earlier into those state variable, and then this is the bid function which we were using to bid. So we are providing the amount, and using this amount it is checking whether the block timestamp, like when you are trying to bid, whether the bid like auction is already end or not. If it is not ended, then only you go further step, your bid will be accepted or not based on the bid amount. If bid amount is smaller than the highest bid, it will not be accepted. And it will checks, like all those checks will be done. Like these are the conditions. When you are writing a contract, these are the conditions will be there in the contract. So terms and condition, when we talk about contracts, these are terms and conditions. But this should be precisely written. There should not be any ambiguity. Like in the paper documents, we may have some ambiguity, but when we are writing the contract, it should be precisely written. It should not have any ambiguity in the contract. And this is like how at the end, when you are the highest bidder, it is stored those information into the highest bid and highest bidder state variables. Similarly, this function is withdraw when auction is ended and you are not the highest bidder, you can withdraw your amount using these functions. So several other functions are there, auction end and all those things. So next, when I'm going to talk about parallel execution, I will be talking about these transactions and the input parameters of these transactions. So here we have this transaction, right? This successful transaction. What was the input parameters? And currently these transactions are executing sequentially one after another. So how we can execute more transaction in parallel? Because Ethereum and Bitcoin have very low throughput. Like if you talk about Bitcoin, it is 7 transactions per second. If we talk about Ethereum, it is 35 or 30 transactions per second. So throughput is quite less. So how we can improve the throughput? That is the part of this talk. So contract, I think already we have talked about contracts, so I am skipping this. But how Ethereum works, let's talk about that. So Ethereum node forms a peer-to-peer network. It's a distributed network. There's no centralized control. Like everyone here in the auditorium is like kind of, you can think of as a node in the Ethereum blockchain. To make any change, there need to be a consensus between everyone. Like if someone want to go outside the auditorium, at least more than 51% have to agree on that. Then only that person can open the door and go outside. So that kind of, you can think of as a blockchain where these are the nodes, and any change must be accepted by the majority of the node. So the clients or the user are the external users who are submitting transactions. So they basically submit the transaction, they are calling the function call. This is smart contract function which we have just in bid. So they submit those requests, and these requests go to the peers they are connected with and kept into a pending transaction queue. So when this transaction is kept into the pending transaction queue, these nodes keep on collecting such transactions, and then they start processing those transactions. So they select transaction, create a block, and then execute those transactions and put into the block. So here in this example, you see here like we have 4 peers, and their state is like the consistent state is up to block B3. Everyone is having B3 state. Peer 4 collected those 3 transactions, given it to everyone else, and also started proposing a block. So when it start proposing a block, what it do is it select transaction, execute those transactions based on its local ledger, and compute a state, final state. So Merkle root and that Dr. Amit was talking about. So it compute the final state, keep it into the block, and compute the hash of the block, or putting the previous block hash and solve the proof of a consensus. So assume like peer 4 was the winner of this process, and it broadcasted that block to everyone else. When everyone else received this block, based on their local chain, like their local view of the blockchain, they again execute those transactions which they have received in block B4. And they, based on their execution, they compute the state. They are applying those transactions into their state and they compute the state. And then they compare this state, whatever they have computed, with the state in the block. If they found like the state is same, they accept the block. Because if everyone is in this chain is kind of working as per the protocol, they obviously will get the same state and they accept the block. Otherwise, if someone who is the malicious and proposing a invalid block, they will be caught and the peers will not accept such malicious block and reject that block. So when in the best case, the block will be accepted because the peer was the legitimate peer and proposed the block and everyone accepted that block. So here one important thing is like when everyone is agreed, the block will become part of, not everyone, majority, the consensus is reached, block will become the part of the chain and this block will be accepted. So what's the bottleneck here? Like in the existing blockchain platform like Ethereum, Bitcoin, these transactions are executed one after another. And that's the requirement, like it should be serializable. But having the multi-core system or resources, this transaction are still executed sequentially. And this lead to the poor throughput, like throughput is quite less. That is one of the challenge, like transaction throughput or scalability, you can say. Scalability is the, if we talk about scalability, it is in the broader sense, transaction execution is one of that limitation. There are other limitations like when number of users or transactions are increasing, how system will be able to handle. When number of nodes are increasing, how system will behave, like whether it is slowing down or when the data is increasing, how to handle that. But transaction throughput is one of the requirement which directly impact the user experience. Because let's say if you have submitted a transaction and you are at a retail store and that store is using blockchain technology and you submitted a transaction to purchase something, and that transaction will take 10 minutes or 15 minutes or more time, then you can't wait there, right? You want your transaction to be processed faster. So when number of user or requests are increasing, system have to process more transactions faster way. So the throughput is one challenge there. Other challenges like consensus protocol, communication protocol, and those things are there, but how we can improve the execution of transaction via parallelism. So when two transactions, let's say transaction T1 is transferring some amount to user 1 to user 2, and transaction 2 is transferring to user 3 to user 4, they are completely operating on different data item. They are touching different data. So can we execute those two transactions in parallel rather than waiting or executing them sequentially using the resources available with the system? So this is one example, like the coin transfer example, where we are transferring, the sender is sending some amount to the receiver, and it checks, the function will check like whether the amount, the sender's amount is sufficient or not. If sender amount is not sufficient, the transaction will not succeed. Otherwise, the sender balance will be deducted and receiver will be credited. So here in this example, we have two transactions. T1 is transferring A to B $10, T2 is transferring C to D $20, and these are completely two different transactions operating on different data items. So we can execute them in parallel. So here, the time, if you think going from left to right, it is taking more time for executing these two transactions. But when we execute these two transactions in overlap manner, ensuring that there is no violation of the serializability and this thing, we can process more number of transactions. Yeah. So when we try to execute transaction in parallel, there are many other challenges. Like existing platform, if you talk about Ethereum, it don't have a parallel execution support. Like Ethereum virtual machine is completely single-threaded execution. You can't execute more transaction in parallel. System is designed that way. So to execute transaction in parallel, we need either the Ethereum virtual machine is multi-threaded or the platform which is executing transaction in parallel somehow. So transaction may have conflicting accesses. Again, when two transaction, like double spending is possible. I'm transferring $100 to Dr. Sham Sundar and I'm transferring $100 to someone else, and I have a total 100 rupees. So if you're executing those transactions in parallel, it may possible that the double spending is possible. So we have to make sure those conflicting accesses should be executed sequentially. So yeah, non-deterministic parallel execution of transaction may lead to the rejection of a valid block. I will talk about this later on. And the malicious miners problem. So with the concurrent execution, if a miner is malicious, they play with the block and try to achieve the double spending. So we have to be very cautious about those things. So the first challenge is like identifying the conflict at runtime, and because many blockchains don't provide the data the transaction is accessing, like the Ethereum, the solidity is during complete language, and it may have conditions and various control flow when transactions are executed. So we don't know whether the transaction at the like static time, we don't know what state variables or accounts they are touching. So we have to need some mechanism that can detect those conflicts during the execution. If we use the traditional database parallel execution concurrency mechanism like logs and these things, and if we use those logs improperly in Ethereum or any blockchain, that may lead to deadlock and blockchain may become to a halt. So we have to be very cautious. We can't directly use logs there. Discovering an equivalent sequential schedule or serial schedule is important while executing those transactions. So here, if we talk about centralized system and the concurrency mechanism, there is only one server that is taking care of the execution. But when it comes to the blockchain, there are multiple nodes. And when miner or the block proposer is executing transaction, it may execute those transactions parallelly in different order, and then validator may execute in different order. So we have to make sure whatever order that miner have executed, all the validator also follow that order. So and when executing transaction, we have to make sure it should be equivalent to some sequential schedule, or it should be as if we are executing transaction sequentially after one after another. If let's say one validator don't have the parallel execution platforms or multi-threaded system, it must be able to execute those transactions sequentially and should lead to the same state as what the miner have reached to accept a valid block. So one of the concurrency control mechanism, which is known as software transactional memory, that is being used in the others traditional systems. We can use one of such system to identify or to mitigate those challenges which I was just talking about. But the important challenge is like, let's say miner is proposing a block and executing those transactions parallelly and giving it to the validator. So here we have two transactions. T1 is transferring A to B $10, T2 is transferring B to A $20. So it may possible like at the block proposer, transaction T1 is executed such that T1 is followed by T2 in the sequential schedule. So the final state, if you see here, T1 is transferring A to B $10. So after transferring $10, its final state must become 0. And when B is transferring T2 to A $20, so after the transaction 2 is successful, the B's final state should be 0, and those $20 will be transferred to A. So here you can notice AB and BA, so the same account. I'm transferring to you and you are transferring more money to me. So that way here, if the execution order is T1 followed by T2, this is the final state at the block proposer or the miner. When executed by the validator, let's say miner haven't provided any information and validator is executing them T2 followed by T1. So though the block was the valid block, it may possible T1 is trying to transfer B to A $20 and B don't have sufficient balance into his account. I hope it is visible. Yeah, okay. So yeah, so if in this order, if validator execute T2 followed by T1, T2 will be aborted, only transaction T1 will succeed. And though the block proposer was the legitimate block proposer, its block was rejected. And that's the concurrency issue when transactions are executed parallelly to increase the throughput. So what can be the solution? So one solution can be like block proposer when executing this transaction. For conflicting transaction, it records the information into form of a block graph or a graph. So here, the block proposer executed transaction T1 and then T2. So it records that information into the block and give this entire block with the final state to the validator. When validator receives this block, it knows like a miner have executed T1 followed by T2, so it respects that order and execute transaction in that order, so that it also reaches to the same state here. But this leads to another problem, which is kind of like this block proposer can be a malicious block proposer, and it want to achieve double spending for some benefit. So what it do is it do not provide this dependency information and propose this block. So again, the same thing like when two transactions, this T1 and T2 executed parallelly, it may possible the same account will be detected 2 times. Though here this example is slightly different. Here we have A1 is transferring A to B $10, T2 is transferring A to C $5. So A have only 10 rupees and it try to spend 15 rupees. Because of concurrency, it may possible it is able to transfer those 15 rupees. So to mitigate this issue, like the validator when executing, it need to identify there were supposed to be one dependency which was not provided by the miner, and because of that I am executing those transactions in parallel. So it have to identify those cases and reject such malicious block proposed by the malicious miner. So yeah, there are different approaches. One of the approach is like statistical analysis based parallel execution. So this technique require all the access information, like what are the account a transaction is going to access. This is practically implemented now in Solana blockchain and even Hyperledger Sawtooth. And there are a couple of more blockchains which employ this technique there to execute transaction in parallel. So what this technique basically do is it select all those transactions, their access information, like what are the account they are accessing, and then schedule those transactions which are independent into parallel, and those transactions which are dependent sequentially one after another. One of the approach which we have proposed is like using those transactions and analyzing those transactions to prepare a schedule. We follow a leader-follower approach where leader prepare those schedule for the execution. This is a kind of distributed community. What we have done is like, let's say we have a single node in the blockchain network and it have more power to execute the transaction. So we use that distributed compute power of the system. So if you think like when a blockchain network is growing and there are more number of transactions that are coming to the individual node, they can employ their cluster mechanism to process those transactions and to do different tasks like broadcasting and those different blockchain tasks. Yeah. So the leader group that block transaction into independent shards or different independent groups of transaction, like all the transactions which are dependent on each other accessing the same account will be kept into one shard or one group. Similarly, those transactions which is dependent on another account, they are accessing another set of accounts, they will be kept into another group, and these two groups will be executed in parallel. So this is transaction execution sharding. This is not key value sharding or the blockchain node sharding. It is transaction execution sharding where different transactions are grouped into different sets and then executed in parallel. So here is one example of that. I hope it is visible. So we have 9 transactions and their access information is available. So by using those access information, we generated 3 shards. Shard 1 is having A1, A3, A1, A8, and A2, A3. So here, if you notice, they are accessing at least one common account in between all those transactions. Similarly, there is shard 2 and shard 3. When these shards are given to the followers, you can think of a different compute machine which is executing those transactions sequentially one after another. But all these shards are executed in parallel. So when a community is acting as a miner, there will be transaction in the pending transaction queue, the leader, one of the node in the cluster, set of cluster, one of them will be leader. It select the pending transaction, it perform the statistical analysis and create different groups and give it to the different followers. It may possible like we have more number of shards than the follower, so the leader will load balance those so that we will perfectly load balance and every follower will be almost executing the same workload and the execution will be faster. So here if you think like there are 100 transactions and if those 100 transactions executed one after another, it may be like, for example, it's taking 100 seconds. And let's say we shard those transactions into 10 different shards and all those 10 shards are executed one after parallelly, but internally sequentially. So those 10 will be executed parallelly, so 10 seconds, somewhat, 10 or 15 seconds. So we reduce 100 seconds to the just 10 seconds. So more transactions we are able to process in parallel. So when miner acting as a mining community internally, it execute those transactions, compute the state, and then propose that block to the validator community. So here those transactions will have their order, the sequential order which the miner will propose based on this shard by shard. Internally, those shards are executed one after another. So if a validator community don't have multi-core resources or cluster resources, they can simply execute them sequentially one after another and reach to the same state. This is the case like when a validator community, when they receive such a block, again they will have a leader and the leader will again perform the sharding. Here we are not providing any information to the block because the statistical analysis always lead to the same shards. Because they also have the transaction, they can perform the statistical analysis and they get the same shards, same number of shards and execute them in parallel. So the thing is, though they are executing in parallel, within each shard, those transactions are executed sequentially one after another. So it may possible like those transactions further can be executed parallelly. Like for the example, we were taking 10 transactions, one after another, 10 seconds. So can we execute those transactions further in parallel without losing any leading to any issue? So that's where like the runtime technique come into picture, where we will use the multi-core resources available within the single machine to run the transaction in parallel through, and at the runtime they detect if there is any conflict, and if conflict is there, they resolve the conflict based on the transaction order and then execute them in parallel. If two transactions T1 and T2 are dependent, they will ensure they will be executed T1 followed by T2. But it may possible those two transactions are accessing more number of data items. So the data item they are not conflicting with can be executed in parallel, and those will be recorded into their state. So STM I was talking about, like what is software transactional memory system. It is concurrency mechanism where the programmer need not to worry about low level details like date logs or priority inversion or many things which may be there if we execute the transaction in parallel using traditional log-based systems. So it exposes some API, like it gives you some functions, you use those functions and write your program such that it can be executed in parallel, and you need not to worry about the background processing. It will make sure your transaction will be executed parallelly without violating any consistency thing. Yeah. So by employing the STM system, we can execute more number of transactions in parallel. Yeah. So the OptiSmart approach is that so this approach involves more things, like in a block there may be many transactions. Some of those transactions may not be dependent on any other transactions. So identifying those transactions and keeping them in, they can be executed in any order because they are not conflicting and they will lead to the same state, but there may be transactions which are dependent. So for dependent transaction, it records the information to the form of the graph that we were talking about, and then that block will be given to the validator. Like you have a concurrent transaction, set of transactions that can be executed in any order, and there is a set of transactions that must be follow that graph order. So when this block is given to the validator, they will use that information to execute transaction in parallel. So STMs are like convenient programming paradigm for programmers to write the concurrent program. Here are some of the functions I was talking about, like STM begin, STM read, STM write, STM try commit, and STM abort. So these are the functions that will be used by the programmers to write the concurrent program. And there can be different protocol in the STM itself, like basic timestamp ordering protocol or multi-version timestamp ordering protocol. I'm not going into much detail of those, but these are the protocol which is used to execute the transaction in parallel. So in the beginning, when a miner start proposing a block, is select all the transaction, keep them in a concurrent bin, or like there's a bin where it put all the transaction and start executing those transactions. At the time, if it identifies that two transactions are conflicting, it remove those transactions from the concurrent bin and add into the block graph. Like these two transactions are conflicting, they should be executed in this order. I'm executing them T1 followed by T2 or so. So at the end, when this execution ends at the miner, it will have a set of transaction which is in the concurrent bin, set of transaction in the block graph, and the state after the execution. It put all those information into the block. There are more information like how the conflicts are identified in the read-write STM or multi-version read-write STM that may be very difficult to understand at this point for the audience, so I'm skipping this thing. But you can think of, there are transactions which can be executed in parallel. There are set of transactions that should be executed in sequential order in the graph. So this information will be given to the validator. Here is one example where we have three transactions, T0, T3, and T7. So this shows how these conflicts are recorded. So if you notice here, transaction T3 and T7 are operating on the same account A. T3 is writing to that account and T7 is reading. So if T7 executed before T3, it will read different value. And if it execute after T3, it will read different value which is written by the T3. So this thing should be recorded into the block, because if this transaction is given to the validator and if he execute T7 before T3, it is getting different value and it may reject such a valid block. So all those information should be recorded into the block, and this shows like how those information is recorded at the time of execution at the miner. So let's assume that block is given. Here we have 9 transactions or something. So this is the concurrent bin which is consisting all those transactions, and this is the graph which is recording those transaction dependencies. So at the validator, it will be two-phase execution. All the nodes have their validator, multi-threaded validator. They first execute concurrent bin concurrently, like all this transaction. 6 transactions will be executed parallelly. Then they execute through the block graph. So one of the thread or the process will claim the transaction in the graph and execute it. So here, transaction 1, transaction 2, and transaction 6 are conflicting, and T2 and T6 is dependent on T1. When T1 executed, T2 and T6 can be executed in parallel. So after the execution of T1, T2 and T6 can be executed in parallel. So if there is one way, like all these transactions are executed sequentially, this is another way to execute those transactions in parallel and to accept more transactions, process more transactions in parallel. So when we talk about smart contract, this there can be value transfer, and which is simply currency transfer. These are micro transactions and small transactions which take less time. But in supply chain or some complex use cases, this transaction may be a larger logic which is taking time in seconds or something for processing. So there, if such transactions are there in the block, it is taking more time. And if we are processing those transactions in parallel, we can process more transactions efficiently through the parallel execution approaches. So yeah, there are a couple of related work there already, so the Dickerson et al. Was the first person who proposed this idea using Scala STM, and there were other solutions, and we have proposed the solution after them. And after this, there were a lot of innovation in the blockchain, like Aptos blockchain. They have proposed block STM-based approach, which is STM-based approach basically, and they were able to process 160K transactions per second in their experiments. So in Ethereum, it is 35 transactions, and they are processing 160K transactions per second, like huge change. And that's what required, like if we talk about Visa or other existing credit card system, this transaction processing, they are processing thousands of transactions, like 30 or 40 transactions per second. So if Ethereum or any blockchain want to be able to process that many transactions and to become a to be a everyday use case of everyone started using blockchain technology, there will be a lot of transactions, and to process those transactions, system should be able to handle and process those transactions faster. Otherwise, transaction will keep on waiting in pending queue, and at the end it will be rejected. So these parallelization approaches are kind of helping there to make the technology versatile to be accepted in real-time cases. These are the guidelines, may be helpful for the programmer, but not for the audience, when they are thinking of implementing these techniques into the blockchain platform. So I'm skipping this. So I'm open to any questions if you have, in general also, and on the talk also. Yeah. You are not audible. Yeah, he's coming. Yeah.
Hi, can you revisit that simple auction contract?
Yes. Yeah.
So this essentially is a program to conduct an auction?
Yeah, it is a program to conduct a very simple auction contract. Like you have a commodity and you want it to be auctioned. Like there are multiple bidders in the auditorium. They are bidding for that particular item. Let's say I want to sell my system. So I put this system information in the blockchain platform, and that is recorded into the contract. And there will be a bidder which is putting their bid on getting this this particular product. Yeah. Each? All bids. All increasing bid. Like
when we talk of an auction, it is usually done on a centralized system, each bidder getting the same opportunity. There is no sequential bidding happening. Anyone who makes a higher bid, anyone randomly can come and bid, right?
Yeah, that is one case.
So it is getting registered one over the other.
Yeah, that is one case. Like the case you are explaining is like there are multiple bidders. They are putting their bids. and the auction is telling them this is the highest bidder. Okay? So here you don't have transparency, right? You don't know whether you was actually the right bidder, right? And you won. You don't have the information about other bidders. But when you go to the blockchain, right? So when you are putting your bids, that information is recorded. So I understand like the privacy is one concern, and that can be handled through the other implementing those perspective there, like your bid will not be revealed until the point bid is ended, like the auction is ended. So those things can be done. This is just one use case, like showing like how this bid is done. So like all the bids, if it is going through the blockchain platform, that will be recorded as a transaction for sure.
It would be compiled on different nodes, wouldn't it? In case it's going to a blockchain,
Can you come again?
would the auction be running on a single system, single particular
No,
node,
no,
or
no,
would
no,
it be
no, no, no,
decentralized running on multiple nodes?
So it is executed in blockchain platform. This is not on centralized system. So this contract is deployed into the blockchain, right? So when there is a bid is coming, a user is initiating a transaction, I want to bid this much amount, right? So that is one transaction. This transaction will be given to all the nodes in the network. When a block is proposed, this block will be given to everyone else to validate. So they verify the transaction, like this user has initiated transaction and this is the bid amount from that user.
Has it been done anywhere?
Yeah, it is done. Right?
Okay. It's just a use case, or it's been implemented somewhere?
This is one use case. This can practically be deployed, right? This can be done by writing a contract. Non-fungible tokens, yeah. Yeah.
So the NFTs which you have heard, all the uh, CryptoPunks and CyberKitties and all of those are the same bid contract, much more complex. But that is what is happening there, right?
By the way, this is very simple example, just to give you an intuition about like how this auction is done. It can be written as a very complex example as well. Yeah.
Yeah.
So non-fungible tokens, like let's say an artist have its art and it put it into the blockchain for the auction, that can be done, right? So there this kind of auction is done.
Yeah,
Please.
thank you. When you say the others will validate each of those bids, who are these validators?
So you have a blockchain platform, right? One of the node is proposing a block, right? It receives the transaction, it proposes a block.
Yeah.
So everyone else, apart from that node, the block proposer, is the validator. They validate the transaction, the block proposed by the miner.
So
proposed.
if it's a competitive environment and there are 10 bidders, what if some of the bidders do not validate the bids made by others? What happens?
So bidder need not to validate the other's bid, right? It is the platform where the node. So you can think like you are a user, okay? So bidders are user.
Yeah.
And then there is a blockchain platform run by, let's say, 10 different organization part of that platform. Let's say finance organization is there, banking sector is there. All those are part of the blockchain platform, okay?
Right.
So when users submitting those transactions, these participants of the blockchain participant, they are validating. And the user, bidders are submitting their request. So you have this contract deployed there. This is the application, right? Here you can see the platform, the user interface I have shown here, where they are putting their bid.
Right.
So you have that part where you can bid. You are using your application, you are bidding. So in the background, there is a transaction initiated. That transaction will be go to the one of the node, blockchain node. So that node will give it to everyone else in the network, and one of them will be proposing a block. So when they propose a block, everyone else, like if there are 10 nodes, okay, so one of them is proposing, other 9 will validate it. So when a majority agrees on that, okay, this is a right transaction, and a bidder put this bid, and he is actually the winner, everyone will agree on that. Okay, right bid, so this is the winner of the auction.
Okay, and just, yeah. Okay. Okay, so could you have a blockchain without a validator? Okay, at least one validator.
Transparency. Yeah. 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 Okay.
See, validation is done during the auction process or after the auction is done. Because anybody who gives a bid, his name is not proposed in an auction. Only the price, who has proposed, what is the latest price. So
Can you
one
come
has
again?
to-
Can you come again?
No, one has to validate other one's auction price, whether it's a valid bid or not.
Yes.
But that shows that this person has bid what amount it is. That is a confidential thing. Until unless the whole auction process is completed, who is bidding is not known.
Yeah.
At the end of the auction process, who wins it, that needs to be known.
Yeah, so that is, I understood that is one of the use case, there is no privacy in this particular example. I didn't put any privacy because here there are other functions where the person, the bidder can know what is the highest bid at this point in time. Okay, so this is very simple use case, but the privacy concern, like there are different bidders and they don't want to reveal their identity till the end of the auction. This can be encoded into the contract itself, and the contract will be written that way, like the other person will not be able to know who was the previous bidder, what was his bid. So that thing need to be written into the code. But this is a very simple use case where these functions are provided itself, like you can know who is the beneficiary at this point in time. So I just simply use one use case to give you an intuition, like this is how a contract looks like and how it records the conditions and what is the function of those terms and conditions. So you have your terms and condition in record and then deploy the contract and interact with that contract. So when auction end, you know who is the beneficiary, who is the winner, and then at that time it can reveal who was the all the beneficiary details also, if you wish to know. Yeah.
So, correct. No,
Yeah.
you just
Agree.
no. Just take this as a use case to just explain what a smart contract is. But you need to understand there are two things you're validating right now. One, you're validating, which is a business logic. Who the validator is the validating amount higher than the previous bidder and all of those. That's a business logic, right? And then there is a blockchain-based consensus which is happening to understand that there is no double spend, there is privacy, all of those which are taken care of. So the blockchain-based consensus which is happening is at a platform layer, which is happening by a validator and notary and all of those which are technical. And the business level validation is happening based on the smart contract which is written as certain set of if and then conditions. So take them as two different layers for you to worry about. And think of this as just an example. Don't go into the schematics of why is this happening. This was just one of those.
Come again? Right now I don't have, but I can share with you. I will find out and will share it with you. Yeah.
Sir, one question for you. You mentioned that validity of the bidder, whether once a person is bidding, whether the bidder is, whether his bid is valid or not, that will be done at the blockchain level itself.
Yes.
Means whether the bidder is genuine. Suppose, for example, a bid is thrown and the value of the, means the one person has bidded, say, $1 million USD, and there is another bidder who may not be capable of 1 million USD, and if he is bidding, say, 110 million USD, then is that bid valid or not? Will it be verified by the blockchain itself?
So if you had oracles available which could check his credit scores, or if he could check his bank account details, could have been done and said that before you bid or when you bid, we will do that check, and then that is when we will authenticate and say this bid is valid or not. So those could be written on the code. Right now what he is showing is a very simple example of your smart contract. Just to show you, because from morning we are talking about so many smart contracts, no one has really seen a smart contract. We thought we'll show you a green screen with some geeky code on it so that you guys can understand it. Yeah.
Just want to ask one thing.
Yeah,
How do you
thank you.
encapsulate subjective conditions in a smart contract? Subjective clauses.
it depends, right? How you are encoding them, right? So another thing like is he was talking about like oracles, right? Any external things which want to be like, so blockchain completely runs in isolation. They not have anything that they can interact with external world, right? So there is a requirement of oracles that provide that information to the blockchain network. Like this is a legitimate information, you process it. So when it goes to the blockchain, they can process, they can understand, okay, this was the correct input provided by the oracles and we can trust it. Otherwise, the system completely run in isolation. They will not be able to interact with the external world. There's a requirement of input oracles, there's a requirement of output oracles, which take the information from the blockchain network and give the external world. So there is oracle interface is required there.
No, so in cases of disputes, so
Yeah.
if this contract or this bid leads to a dispute, now would a adjudicating court require your oracles, the smart contract, as well as the, the clauses, subjective clauses? So how will it get to know what all has transpired?
So code is the law, right? Whatever recorded into the contract, it can't be changed. So the blockchain will be able to process only that information. Any dispute outside the blockchain need to be solved externally only. And if the contract is not able to handle those things and you want to change the contract, that require the deployment of the new contract based on the agreement between all the parties.
I think that was a great example. If it's a lot of life in the audiences come up. Like what sir was saying in the morning, garbage in, garbage out. So that's what it is. The code is, that is what it is, right? Garbage in, garbage out. The second thing is, the smart contracts are very deterministic. You can't have a subjective thing. So if 2 plus 2 is 4, 2 plus 2 is 4. And you need to have an end. It can't ever be in a loop or in an undecisive state. If you can't get an answer which is in the deterministic, then you can't write a smart contract. Then you need to do what sir was saying, that you need to have an oracle which is a human oracle. If that is the case, then you bring a human intelligence in it to do it.
No, I think in my impression, his intention was to show how you can scale up the smart, I won't say smart contract, the blockchain platform. Okay, smart contract cannot be scaled up because this is a small thing which happens or the other. So I think, for example, in auction, suppose you want to say anyone can bid, the highest bidder would be chosen. Naturally, none of the bidders should be known to the others, and it cannot come on the, if it comes on the blockchain, it's a problem. In fact, this is something I think people have to understand. In a classic blockchain, everything is public, so this will not work. You have to go for privacy preserving transactions like zero coin or something like that. Otherwise, it will not work. In fact, some of the games, what the exploitation shows is, if I know what is the, like if I play a 1-2 game or 0-1 game, if I know that this is the person he has put 1, because it's already there, I know I will not put that. So that will not work, and that is some of the things what you have to understand. Because it is public, there are some things what you thought it was secret, it is no longer secret. You have to make it a private variable so that it will not be seen to the outside. So these are some things. He showed it, in my opinion. That's why I asked him, you tell what is the problem this solves, because nobody will go through that code or the other. So if a auction, if a simple auction where you have to choose the highest bidder, naturally all the bidders who have bid have to be secretly given the name, and it has to be opened only at the strike of time T1. And now synchronization of time also is a problem in auction, because if somebody just now say it is just like Krishna putting this one, it is not at sunset kind of a thing, it becomes a problem. So these are all things that technologically what can be handled in this smart contract. Like what you said, what would be the dispute? There will be no dispute as far as smart contract is concerned. It's only on the performance, and if you say whether he performed well or not, it does not know. He just performed. So that's all the thing what it is.
Thank you so much, Professor.
Excuse me?
No, for all the practical enterprise requirements, you have to adapt it to many of the requirements. Now you have non-fungible tokens, etc. This, one of the natural protocol on Ethereum was ERC20, what I mentioned. If you use it straight, that one, you will end up in a problem. And lots of money have been pilfered because of that flaw. But you have to see, that is how I said, you have to do a very careful coding. Smart contract is hard, and now you have to say what is law and what is code. You see, what is the difference between privacy and security? Anyone? Or is it privacy security? No, privacy is you can give up your information with your permission. But privacy can be implemented using security measures. But it is not private. For example, your name is not a secret. It is public. It is not even public. It is private. That's how you put a badge to say I am so and so. So there is a difference of the other in a privacy kind of a thing. That's how if I want to do confidentiality, either you have to go privacy preserving blockchain like zero coin, zero cash, and so on and so forth. Like that.
Thank you so much, Professor, and both of you for
yes, sir. One more question. In a forward auction, it once so happened that all the bidders were sitting in a hotel room, and they made a cartel, and they were bidding, and they somehow it was known. Can that type of fraud be detected here?
No.
It cannot be detected because same, maybe different IP addresses. Huh? No, not same point. Same server, then the IP address, it is natural. That can be known. Okay, okay. Right, sir. Thank you.
Yeah. Thank you so much.
I want.
Yeah. So pipelined execution of the smart contract, right? So it's like how, in what context you are saying this? Like within a blockchain execution platform, when these contract transactions are executed, so you are executing them in pipeline way, you can, if they are not having any conflict, right? If they are having conflict, the pipeline will break.
Yes, sir. I am asking about the efficiency of the smart contract execution in parallel and pipelining execution of smart contract.
So I haven't done any experiment on pipelining execution,
Okay.
but yeah, that is kind of one thing. But it's again challenging, right? Yeah, it's sequence. Where sequence breaks.
Yes, sir.
Yeah.
Time. Yes, sir. Yes. Hmm. Yes, sir. Yes, sir.
Performance.
Yes, sir. Yes, sir. Thank you, sir.
Yeah.
Thank you very much.
Yeah, thank you so much. Yeah, yeah, that's all.
That is called being dot on time because you're almost touching 4. Thanks a lot. We will break for the day, and tomorrow we are meeting at 10 as far as the session starts. And those who are interested in a bit of Pet Puja, they can come a little earlier. Okay.
Thank you so much.
Thank you. Thanks a lot.
Requesting Madhuvan Singh Kumar to hand over the memento to Dr. Parwat Singh Anjana. Thank you all.